video, not picture.
Who's still gone?
I had a couple of people this morning that were doing the ESL testing. No, it was an ESL thing, so they were.
Oh, wasn't there also a math test?
Yes,
I
it
didn't hear
was.
that today. I don't think so.
First to third hour.
All right. I don't know if it was today. It was today? Okay. So here we have the very first day of this chapter. I mentioned the word volt because we were talking about the cell potential difference and what it is in terms of redox reaction. And I had defined a volt, which is a unit. A volt is a compound unit. It's made up of joules per coulomb. So a volt is the same thing as joule per coulomb. Now, joule is the unit that we use for energy or work, and coulomb is the unit that we use for electrical charge. Now, cell potential is, we use this Greek letter epsilon, where the Zumwalt's use that scripted E. Just some different looking E is fine for that. Cell potential is defined as work per charge. Now, unfortunately, whoever had decided back a long time ago what symbols should be used for quantities, they decided that they should use Q for heat, like transfer of heat. We've used the equation Q equals mc delta T. But then it would be a good idea to use that same letter for something completely different. So we now have a Q, the same letter, lowercase, that represents charge. Like the charge that an electron would have. It's electrical charge. Oh, yellow, that's nice. How about we go with that? So this is a simple relationship that we have. It's really just based on what the unit volt means. The next thing I want to do is try to define charge. Now, charge is not really a definable quantity. We know that electrons have a negative charge, and in protons and neutrons, there are these little tiny charged things called quarks. But what is charge? Well, this is a terrible definition of charge, but we're going to use it anyway. What are you doing?
He's trying to crush up his water bubble. He doesn't want to do it next to the
Yeah, thanks. Charge is measured in coulombs, but that doesn't really give away what charge is. And the next part of it is 1 mole of electrons would have a charge of 96,485 coulombs. So even though that doesn't define what charge is or really mean anything, at least it gives us some relationship. 1 electron is so small, one single electron can go flying even through your body and you wouldn't know it, you wouldn't feel anything because they're so tiny. But a mole of electrons, that's something that we can deal with. Keep in mind that you can't have a container that has a mole of electrons in it. We don't build up charge. And you can't, save charge. You kind of can, but that's not conventional. So this quantity, 96,485 coulombs, you do need to know that. That's a conversion factor that we're going to have to know. It's called Faraday's constant. The number represents Faraday's constant. Now, Faraday's constant uses the symbol F. So you're going to see F in some of our equations. That's what that means. So F represents a relationship. That many coulombs for every 1 mole of electrons. Is it okay?
Yeah.
Ring is not a metal. Oh. Okay, so what I'm going to do is I'm going to just do a little algebra substitution. This is my definition of Q. According to this definition, Q, remember, Q represents the quantity of electrical charge, is equal to N. N, as always, represents the number of moles. In this case, though, it's moles of electrons. And then F is Faraday's constant. So, like if I have 2 moles of electrons, I multiply 2 times Faraday's constant, that would tell me how much charge I have. If I have 1 mole of electrons, I have 1 times Faraday's constant. So Q is going to be replaced by NF. So that means that when we have this thing, epsilon equals work over Q, that's the same thing as work over NF. Now look at the title of the slide. We're looking at the relationship between cell potential, that's that epsilon, and free energy. What symbol do you think of when I say free energy?
Gibbs triangle.
You got it. Delta G. Delta G.
Oh.
So we need to bring that one back. Delta G is the free energy available. So when a system has a certain amount of energy that it can use, that's its free energy. It consists of two different things. The enthalpy, the amount of heat energy that it has stored that it can give off, and the energy called entropy. It has to do with the arrangement of the particles. Right? So delta G defines how much work can be done. That's what delta G is. It's the amount of energy that's available for doing work by a system. When work is done on the surroundings, it's defined conventionally as negative. We did that before, like when a system expands, it's doing work pushing on the surroundings, so work is negative P delta V. So that's why I had that negative sign in there. The delta G is negative work, just by our sign convention. So that means this. I'm going to replace work here with delta G and get to something that we're actually going to use and kind of package. And that would be this relationship right here. Because the cell potential equals negative delta G over NF, just rearranging things, we come up with this. Delta G equals negative NF epsilon. I don't know.
I don't swallow anything.
I don't either.
Oh yeah, it's all kind of good stuff.
Oh, hand sanitizer. Now delta G, we've had several equations that delta G is in. Delta G equals delta H minus T delta S. Delta G equals negative RT ln of K. Among others, we also have delta G equals negative NF epsilon. Delta G is a pretty significant component in this course. In fact, it may be the central concept of the entire course, is delta G. Delta G pretty much drives everything that's natural. So we're going to do an example problem on the next page. Let's just make sure that we understand what this involves, though. When we calculate the delta G for a reaction, the N right here, remember N represents moles, but specifically is moles of electrons. Now we're talking about redox reactions. The oxidizing thing is giving off electrons, the reducing thing is taking in electrons. The number of electrons given off and taken in, that's the N value, moles of electrons. The F is Faraday's constant, that's that number. And then the epsilon is, of course, the cell potential. So this example, it looks harmless enough. It's just a short little thing. But take a look at it. Calculate the maximum amount of work that can be obtained. In other words, delta G, that provides the energy for the amount of work that can be done, from the galvanic cell described by the following equation. And then we have that chemical equation. That chemical equation's got some nasty to it.
What are the numbers?
What numbers? Yeah, if I gave you the cell potential, that would be nice. But I didn't. So we have to figure it out. When you're finding the cell potential, you need the thing that's reducing, its reduction potential, and the thing that's oxidizing, you need its oxidation potential, and then you need to add them together. When I look at this equation, the question is, who's oxidizing and who's reducing? Every single one of these four terms has chlorine in it. It's going to turn out that chlorine oxidizes and chlorine reduces. Now, there's a couple options you have. You can do like we've always done, and find the oxidation number of the chlorine in all of these. That works. It may not be obvious though what is, like if this is, this Cl is a positive 3, and this Cl is a positive 4, and this Cl is a negative 1. Well, what is this chlorine doing? Is it oxidizing to that, or is it reducing to that? And what about that one? If that one's oxidizing, is that one reducing? So here's what we do. That paper that I gave you, either I gave it to you Monday or just now, this reduction potential table, you're just going to kind of scan through this thing and see which of these combinations are there. So can you find anything that resembles what's on here on the paper?
Probably.
Tell me when you do. That is almost halfway down the left side. I'll put my finger on it so you can see where it is. Right there. Can you find that? My finger's right next to it. Almost halfway down.
Yes. 1.36.
That's our, and so we have that happening on here. This is a reduction. So I'll call that reduction, R-E-D. And then the reduction potential, what was it, 1.36, right?
Yep.
Okay. What about ClO2 negative making ClO2 neutral? Raj? 0.954. Everybody look at that one where it says 0.954 for the reduction potential. Raj, what else you want to tell me about that half reaction? Say it louder. You have to flip the entire equation because we don't, and look at, on the paper it says neutral ClO2 yields ClO2 negative. That's not what we have up here. The neutral CO2 is over on the right. Why is it like that? All these are written as reductions. You can have two reductions happening, so one of them has to be flipped. Very good. Yeah, exactly. So, yeah, you are going to have to find one of them as an oxidation, which means it's going to have to be the reverse of what's on the paper. So this going to this is an oxidation, and it has an oxidation potential of negative 0.954. On the paper it was positive, but remember it got turned around. So the oxidation potential is the opposite sign too. Yeah? Volts. Both those are in volts.
What do we
So-
do with this? What do we do?
Well, the question is, what is delta G? They're asking what's the maximum amount of work. That means delta G. So we're going to use this equation. Delta G equals negative NF epsilon. We now know the epsilon. Just add those two together. And then the F, remember F was on the previous slide. It was that 96,000 number. It's a constant. The N is what? It's the number of moles of electrons that are transferred. Now, I'm just going to take a moment. This doesn't take long. Over to the side, let's take a look at this. Our oxidation was the chlorite, ClO2 negative, giving off electron. It was making ClO2 plus an electron. And then the reduction was Cl2 plus 2 electrons makes 2 Cl negative. I just took those right off the paper. What do I do when I want to add these two together to get that equation? Yeah, you need to have the number of electrons cancel out. Remember, we've done that a lot now. We have to multiply the top one by 2. When we do that, the oxidation is going to give off 2 electrons. The reduction is going to take in 2 electrons. Now I can add them together. That 2 electrons, that's our N value. That's not bad. Okay, so let's see what it looks like. Delta G equals, I'm going to do just about the whole line because I'm going to include the units too. The N. N is 2, and it's first negative. Don't forget the negative sign. Negative 2 moles of electrons times the F. F is 96,485. By the way, if you want to just memorize that as 96,500, that's fine. 96,500, if you can remember that.
Yeah, how do we?
That's
how
totally
is it
different sig figs, though. That is just totally different sig figs.
Nope. The 2 is exact.
Oh, yeah.
This is 5 sig figs, but then our cell potential is going to wind up being 2 every time. So just round to 2 sig figs.
How do we get 2 volts?
Oh, that's exactly what you said. The oxidation gives off 2 electrons, the reduction takes in 2 electrons, so the N is 2. This reaction would travel,
How much
would
is transferring?
transfer 2 electrons. Yeah. Okay, so the unit on 96,485, this is Faraday's constant, remember. It would be how many coulombs are in every mole of electrons. So you should look at this, and there's something that cancels out. You see it? See how the moles of electrons cancel out with that? Yeah, they should. And then finally we have our epsilon, which is the cell potential. That plus that is going to give us 0.41. You see the 0.41? Yeah. I'm just going to stop at the 1. Now remember, that's volts, and the volts is joules per coulomb. So something else cancels out. So I have the moles of electrons canceling, the coulombs canceling, and we're left with joules. And that's what the unit of delta G is, joules. Now delta G, traditionally, we express it as kilojoules. Now when you multiply these 3 things together, you're going to get a big number because of that thing. So it's normal to just round it to kilojoules. So when you do the multiplication, it gives you negative 79 kilojoules. Oh yeah, the formula is negative NF epsilon. And all 3 of those were positive, so the answer winds up being negative. Anybody have any questions about that? So there'll be some exercises like this in the book. I gave you one that was not a pretty one to try to dissect and figure out what the 2 half reactions were. Generally, it's easier than this. I gave you a nasty one. Now the next slide, we did something like this similar not that long ago. I gave you 5 bases, or maybe it was 4 bases, and I asked you, hey, rank the strength of these bases. All you had was the Ka values. You might remember doing that. This time, I'm going to give you 5 ions and molecules. Can you rank them in the order from most, well, not most, but the best reducer to the worst reducer? Does this paper help?
Yes.
Yeah, for sure. You need the paper. You can't do it without the paper.
Do you use absolute value?
No, you have to keep the sign. Because negative means it's not good at reducing.
Huh?
If it's a negative value, it means it's not good at reducing. So everything below hydrogen in the right column is not going to favorably reduce.
So anything that's like whatever's the most positive is the best.
Yes, yeah, that's the best one.
So H2O.
No.
What?
Do all of them.
Here's the strongest. This is so hard. Where's the H2O tree?
Oh yeah.
Even if it was H2O2, it's still really
Oh, that would be negative. Oh yeah, I guess.
Yeah.
No, H2O2 is like the 4th from the top.
Yeah, is it? Oh, yeah, it is. Oh, reducing the shape of place.
Yeah, the ability to reduce. I just pause. Anybody that's just looking them up on their own.
Yeah, I didn't see H2O. Oh, cool.
It's about the middle of the right column. It's just more, a little bit more than halfway down.
Is it 0.00? No.
What'd you say?
Well, that's like hydrogen
I found
ions
it. It's
from
minus
acid.
0.83.
Yeah.
Okay, let's look for that AU
You could just look up at the board.
now. Or I could do the work.
This is not work. Don't think you're any smarter because you're looking at a list.
Yes, you are. I want you to get used to this table.
0.99.
Oh, I'm so proud of you. You went to the table. You are set for this test.
would you ask me for help?
Hell, man. I'm stuck it out.
Okay, so which of these is the best at reducing?
I would agree.
The most positive one. And the worst at reducing would be the K, because it gets the most negative. So just go from the most positive down to the most negative potential. And so here's our ranking. I'm sure you have the right ranking too. Once you come up with the
This
values,
should be a freebie quiz question.
maybe,
Is this going to
maybe.
be on the quiz though?
Sometimes it's on quiz question.
Eric, you already started that?
But you get no table.
Just wondering.
Yeah, well, you'll have that. Without it, it's going to be hard. Any questions on that? We'll go to the next one. Now, the next one is not, this one was simple, very straightforward. Try this one. Again, here's 5 ions or molecules, but this time,
Kobe, don't
it doesn't seem that bad. Go ahead, do it. And I'm not saying you're going to just be riddled with mistakes, but it's not that easy. These things, all of these you have to find in the products of the reductions.
This is confusing.
It is.
Wait, does that say H minus?
It is. It's called the hydride ion.
You still flip and then find the
Oh!
Yes.
That was,
Flip the reaction, change the sign, and then rank them.
Still, what's the highest number?
Yep.
So not F.
No, definitely not a.
something is really fun. Are we supposed to like flip it?
Yes.
How come we don't flip the CU plus?
1.2?
We did.
Did we? You sure? I just looked
Yeah,
at the
and we're using the half reaction that's right above the hydrogen.
What?
So find hydrogen 0.00 and go to the one above it.
Wait, there's like two.
That's the oxidation of Cu+. You got to find Cu+ in the products.
Oh, because CU is going to. Oh,
Yeah, and then you
I
flip
understand,
it,
I understand.
So it slides in negative 0.16.
Yes, but you have to find an equation that just has H2O in the products. And nothing else. So that's the negative 1.23.
Wait, then why did you use 8.3 in the last one? Point, sorry, 0.83.
Yeah, because the last one, we had to have the reduction of water.
Yeah.
Now, the reduction of water is, you use the way it's written. The water will be a reactant. In the oxidation of water, you got to find water in the products and flip it around.
Because he's bad.
So no, it's supposed to be zero negative, right?
Yeah.
So the iodine is
1.2.
almost
Why
halfway.
isn't it negative 0.16?
You're 0. What?
1.6, the first one.
Negative.
That's what I have, 0.16.
It's negative though, right? Because don't you have to flip
Negative. I didn't put the negative on it. Yes. Thanks.
We're going between
Iodine.
Second to last one.
Yes, the second one.
M.
1.2. What about this?
Products.
Yeah, I thought it was, wait.
Oh, but that's the I.
Yeah, right. You'd have, these are oxidations. You got to turn it around. So the 0.54 is the reduction of iodine. We need the oxidation of iodine. So yeah, you got to use
How
one
does
higher.
0.54 go to -1.2?
No, it doesn't. There's another way.
You sure it is?
Yeah. Check 1.
Yeah, go. It's halfway down the left side. It starts as IO3 and goes to I2, but you got to turn it around.
Oh, so we're flipping the one where that thing is apart. I was flipping the one where. This one, it got hard that way. What is this now? This is oxidizing?
Yeah, we're looking at oxidation. So we rank them the same way. The one with the highest, most positive oxidation potential is the one that's most favorably oxidized. So in this case, there's only one that's positive. That's a hydride ion. Hydride is very interested in getting rid of that outer electron that it has. So that's our first one. And everything else is negative. Huh?
Where's the H plus?
The H plus. That's the 0.00. Did anybody find water in a different half reaction?
Yeah.
I mean, there's a lot of waters on there, but are there other half reactions where there's only water in the products?
Yeah.
Not only.
Yeah, there's one of them. The fourth one down from the beginning.
Yeah.
That is where hydrogen peroxide reduces to make water. So if water is oxidizing, it can oxidize to hydrogen peroxide, but it is not likely. I mean, hydrogen peroxide is really unstable. So if I keep saying hydrogen. If water oxidizes, it's going to oxidize to oxygen, O2. So that's why I chose to use the 1.23 voltage, not the one with peroxide in it. You see what I'm saying on that? I would say in general, don't oxidize water to H2O2. Oxidize it to oxygen. So here are the correctly ranked 5 things. Fluoride ion for sure is the worst. There's nothing that will oxidize fluorine. It totally would resist that against anything.
So we shouldn't use fluoride in our lead?
Huh?
When we do the battery lights?
Yeah, you'd want to use fluoride. Unfortunately, no fluorine allowed.
Oh,
What
why?
about neon?
Dangerous.
It's bad.
It's not. I trust me.
Ba-
Whatever. That's people making up.
All right, well, go ahead then.
Doesn't neon plus reduce
No,
fluorine?
What about
Neon plus. Yeah. Silver plus 2, I hear that's out there too. I had somebody looking up on some chemical suppliers' website. They actually found silver plus 2, but it didn't just have a listed price on it. It said, hey, what's your name and company so we can contact you? You know, sometimes it's not so obvious. Okay, I just have one last slide and then we'll quit for today. Looking at the difference between the cell potential and concentration. This is going to get us to the a calculation.
Yes.
Yeah, I mean the math has been kind of light so far. We can't have that for too long.
I like this drawing.
So I want you to take a look at this reaction. Iron solid reacting with permanganate. Permanganate is really good at reducing. You can see that on your table. So I wonder if we can get permanganate in a store and use it in our battery lab. It's good at reducing. All right. So anyway, the permanganate reduces to Mn plus 2, and the iron oxidizing izes to iron plus 2. This is not a balanced equation, but it's okay. The table that you use, the first word of that table is standard. Standard reduction potentials.
25 degrees.
Right. Everything's going to be at 25 degrees. I'm not changing the temperature even one time in this chapter. But the concentrations matter big time. So if all of our concentrations, even the products, are at 1 molarity, then what you predict will be the voltage of this cell will be the voltage. That's the only time that table will give you the accurate voltage is if all your concentrations are at 1 molarity. And if you have gases, the gas got to be at 1 atmosphere pressure. So if I wanted the voltage of this cell with 1 molarity, I'd just use the table. Now what about, what's going to happen to this cell, the voltage of it, if I kick the permanganate concentration up to 2 molarity? Without any calculation, would the voltage go up or down, or would it not change? I will tell you that cell potential is dependent on concentration, so the not change option is not there. It's either going to go up or down. So if I'm talking about raising the concentration of the reacting thing,
We'll go
We
down.
need more of this, more of
We'll go down.
yeah, it's going to go up.
Oh, really?
Yeah, think about it in terms of like Le Chatelier's principle, and that's the principle I'm going to use to describe. I know this is not an equilibrium reaction, it's just a one-way reaction. But for a reaction in general, if you kick up the amount of reactant that you have, it's going to push the reaction more that way. The reaction goes faster, it proceeds with more energy, or it gives off more energy if it's exothermic. So yeah, if you increase the concentration of reactants, that kicks up the voltage. That's another thing that's good to know as you think about your battery lab. And that's why I make such a big deal about the concentration of some of the reactants, because people recognize, oh man, my voltage is going to be the highest the more concentrated my reactants are. I'll go buy a bottle of 37% hydrogen peroxide. It works great, but it's too dangerous. So that's why I said let's just stick with 10% or less. So yeah, increasing the amount of reactants will increase the, the word I use is favor the forward direction, and it actually would increase the voltage. And then the opposite is also true. That's what I have down here. What if the permanganate is 1 molarity, but I kick up the concentration of the products? If those both go up to 2 molarity. The more products are built up, the less the reaction tends to go to the right. Now, I'm not saying the reaction turns around to go to the left. So look at the arrow. It's only a one-way reaction. But it's going to go to the right with less force, or with less of a push to the right, the more product you have. So I want you to know that. Increasing the reactants creates a higher voltage. Increasing the products causes the forward reaction to be resisted some, so it decreases the voltage. And we're going to calculate how much those changes are tomorrow. I'll have this thing called the Nernst equation that will calculate that. But that's the concept behind it. And I shall hope to see you tomorrow. Don't get sick. Wash your hands frequently. Cover your cough, as they say.
So,
Weekend.